So what we have done so far is we want to do model-driven development of our system. And we know when we do any analysis, we want to perform the analysis upon the models rather than the generated codes. On the other hand, we know how to do data flow testing. How we bridge the gap is what the approach is trying to achieve. However, we actually need a notation to do our experiments. So we introduced a new modeling notation called Booster. And Booster is both object-oriented, so we support the familiar features of classes, attributes, class invariants, and methods. And the second feature is really unique because we are trying to specify the methods or model operations in terms of first-order predicates. We also specify the constraints as invariants, also in first-order predicates. And Booster is actually based upon two formal methods, both Z and B. And this feature is particularly important because when we specify the methods, we want to say what's really the relation between the values before the method and the values after the method. For example, let's say I have one variable called x. Also, x prime is equal to x plus 1. That means the after value of x must be the before value of x plus 1. So that's how we specify the relation between the pre-state and post-state. And essentially, Booster is actually a model compiler. Again, we will have a Booster model at the top level, and we want to generate a working system, for example, SQL database on the model. So this is the first example of Booster. So let's say we have a bi-directional association between two classes. So a staff can have up to 10 students as their supervisees, and a student can have 0 or 1 optional staff as their supervisor. So this is like the bi-directional association, and this is how we specify in Booster syntax. We have class attributes, and in the class staff, we say we have a set of supervisees, and they are of type students. And in the student class, we have the same. And the unique feature of a Booster is we specify some redundant information for the compiler to generate additional codes to maintain the association invariance. In this case, we say the staff is also a supervisor of some other students. We say the student is also one of the supervisees of another staff. We actually give this redundant information to the compiler. So for example, let's say I have a method which will assign a staff to the current students as the new supervisor. This is what the user specified. And the compiler is actually going to generate an additional code to say, I'm also going to add the students into the staff's set of supervisees. So actually, we can maintain on both sides. Okay, let's consider another example. And I actually want to use this example to demonstrate our approach. So again, we have students. We have another two classes called course and degree. A student has up to 8 registered courses, and a course has many students in the registration list. A student has one single degree status, could be PhD, Master of Science, etc. And a degree has up to 250 candidates, students. This is how we specify in Booster. We have a single system, and we have 3 classes, so students, course, and degree. And this is the association I just mentioned, so you can just believe that's correct. And I want to draw your attention to this invariant here. We're saying that for every student, his balance must be between 0 and 1600. Keep this 1600 in mind. We're actually going to manipulate this model constraint very soon. And in the class of degree, we say the candidates can have its cardinality up to. So this square bracket is how we specify the cardinality of the collection, only up to 250. Also keep in mind it's 250. 1600 and 250. Keep these two numbers in mind. Okay, so that's the example. And now we want to specify some model operations. In the student class, let's say we have 2 methods. The first method is to register a degree for students, and the second method is going to charge the students for the registration for the degree. In the first method, we say, so this is the current students. We are actually, so this column here is the set membership operator. So the current students will become one of the members of the degree candidates. The question mark here is just input. So we have some input degree. And then we want to add the students into the post state. See the prime here? That represents the post state value of the candidates. Also, we are also going to charge the processing fee for the students by 1,000. And we are actually going to do this only if the cardinality of the registered courses of the students is larger than 2. So this is the implication of logical combinator. And this ampersand is parallel composition. Just say these predicates must be true at the same time. In the second method, we're actually going to charge students in 2 different circumstances. If the current candidates in the degree is actually larger than 100, we're going to charge the students by this expression. Otherwise, we're going to charge by 800. So let's look at the expressions in red. In this expression here, we say we're going to add the current students into the candidate's attributes. So we are trying to modify their attributes. That's quite obvious. And in this expression here, we are trying to use the value of the cardinality of candidates and then use it to compute the value and then deduct the value from the balance of the students. So we're trying to use it. In here, we're trying to define it. Now, just a very brief slide on how what's the formal semantics for the booster environments. So we kind of consider every attribute is a function, is a relation to be more general. So remember, we have a balance for the students. So that should be a total function from students into integer. And we also have status and candidates, the bi-directional association. So it's from students into degree. Here's from degree to students, and etc. Now, for example, if you want to update the status of the students, we just have to do a relational override. So this is just the formalism behind the scene. Now, so in Booster, we are really considering the attribute function values rather than object values. What we really care is the attributes. So this is how we can adapt the data flow testing technique into the Booster predicates. Right? So this is exactly what I just mentioned. So let's go back to the code fragments here. In this expression, we are trying to modify the attributes candidates. In this expression, we're trying to use the value of the attribute candidates. So we have that. We also have a use. So that really qualifies to be a valid testing case from the data flow point of view. Right? So exactly what I just mentioned, that and use. And now, this is really the Intra-Method usage pattern because we're considering the usage pattern within one single method. But once we get the Intra-Method usage pattern, we may want to create Inter-Method usage pattern by composing the 2 methods together. So this is exactly what we're going to do. So for the attribute candidates, for one method, we know it's going to define it. For another method is going to use it. So we want to have a sequential composition of the both, and then compose them together. So this is the sequential composition combinator in the Booster method, and we really want to apply our data flow testing into the Booster model because we pretty much know what is going to happen. We know in this method we are going to change the value of the attribute candidates, and in this method we are going to use the value of attribute candidates. And if we compose them together, we actually have a def and use usage pattern for candidates. Right? Good. Now we come to the core part of our approach. We have identified the intra-method usage patterns, and we have composed the inter-method usage patterns, and now we want to generate some testing cases. But what do we really expect from the testing cases? So testing cases, okay, since each method is a predicate, so it should make sense the testing cases themselves are also predicates. And this predicate should really guarantee 2 things.